Good day, guys. Today we see the fifth unit in architecture. So this unit deals with parallelism, needs, types, and application and challenges, architecture of parallel system, Finn's classification, and we'll deal with ARM processor and its thumb infrastructure instruction set. Okay, so basically, parallelism is nothing but executing two or more operations at the same time is known as parallelism. Parallel processing is needed to improve computer system performance by executing two or more instructions simultaneously. So a parallel computer is a set of processors that are able to work cooperatively to solve computational problem. Two or more ALUs in CPU can work concurrently to increase throughput. Okay. The goals of parallelism is to increase the computational speed, to reduce the amount of time you wait for the problem to be solved. Second is to increase throughput, the amount of processing that can be accomplished during given interval of time, to improve the performance of computer for given clock speed, and to solve bigger problems that might not fit in the limited memory of a single CPU. So types of parallelism is there are two types of parallelism, hardware and software parallelism. So hardware parallelism is the main objective is to increase the processing speed based on the hardware architecture. We can divide hardware parallelism into two types, processor parallelism and memory parallelism. So in processor parallelism, the computer architecture has multiple nodes, multiple CPUs or multiple sockets, multiple cores and multiple threads. In multiple memory parallelism, shared memory, distributed memory, hybrid distributed shared memory, etc. Sometimes it is also called parallel random access machine, PRAM. It is an abstract model for parallel computation which assumes that all processors operate synchronously under clock under a single clock and are able to randomly access a large shared memory. So what is hardware parallelism? One way to characterize the parallelism is processor in the processor is by the number of instructions issued per machine cycle. So if a processor issues k instructions per machine cycle, then it is called as k issue processor. In modern processor, two or more instruction can be issued by a machine cycle. So conventional processor takes one or more machine cycles to issue a single instruction. These type of processor are called one issue machines with single instruction pipeline in processor. A multiple processor system with built NK issue process should be able to handle a maximum of NK threads of instructions simultaneously. So next is software parallelism. So it is defined by control and data dependence of program. So degree of parallelism is revealed in the parallel program flow graph. So it's a function of algorithm, programming style, and a compiler or optimization. So parallelism program varies during execution. So for example, sequential execution. So in the first pipeline, C equal to D into E is done in pipeline 2, equal to C plus C, and third B plus C, and L plus M, and G divided by 3. So sequential execution in 5 steps, assuming 1 step per statement. So parallel execution, what I can do is I can in one step D and E. In step 2, I can have G and C and also B and C being executed in the second cycle. And in same thing, both are added together. G and E are added together because it is independent. G is divided by E. Then you add L plus M. So if you look at, see, C is addition of D and E, M is G plus C and B plus C. So I can't do C and M, calculate M and A parallelly. So I do C in an individual step At the same time, I calculate M in an individuals, M and A in same step, and also I calculate F in the same step. So I have reduced the clock cycle by 3. So mismatch between software and hardware parallelism. So example is A is L1 into L2 plus L3 into L4. B is L1 into L2 plus minus L3B. So in software parallelism, four load instructions L1, L2, L3, and L4, two multiplication operation X1 and X2, one add instruction plus one subtraction instruction minus. The parallelism varies from 4 to 2. So three cycles. In three cycles, I can do it for mm, 2 parallelisms. So average software parallelism 8 cycles by 3 cycles, which is 8 in divided by 3, which is 2.67. So using two issue processor, the processor can execute one memory access and one arithmetic operation simultaneously. The program must execute in 7 cycles. So the hardware parallelism achieved is 8 by 7. It is clear from this example, the mismatch between software and hardware parallelism. So, an hardware platform of dual processor system, single issue processors are used to execute the same program. 6 processor cycles are needed to execute the 12 instruction by 2 processor. S1 and S2 are inserted store operation, and the L5 and L3 are in two inserted load operation. And the instructions are needed for inter-process communication through sharding. So software parallelism, there are four types: instruction level, task level, data level, and transaction level parallelism. So instruction level parallelism is measure of how many operation can be performed in parallel at the same time. So how many instruction can be executed at the parallel at the same time in a computer. Hmm. Parallel instructions are set of instructions that do not depend on each other for executed. So ILP allows compiler and processor to overlap the instruction execution of multiple units or even change the order of the execution of instructions. So the example is x equal to a plus b, y equal to c minus b, and z equal to x plus y. So calculation of x and y are independent of the values. So both the operation can be concluded in one cycle, whereas third step is done in a separate cycle because x cannot be calculated, z cannot be calculated until x and y are calculated. So you see that each operation can be completed in one cycle, then three operations can be completed in 2 units of time. So ILP is 3 by 2, which is 1 by 5, which is greater than without ILP. Superscalar CPU architecture employs ILP in single processor. So data level parallelism occurs multiple processes in parallel computing environment. It focuses on distributing data across different modes which operate on the data in parallel. Instruction from single stream operate concurrently on a several data. So let us say we want to sum all the elements of a given array. So in this case, what we'll do is if we execute this job as a data parallel job on 4 process, the time taken would reduce by n by 4 into TA, merging overhead times. So in DLP, in matrix multiplication, so each multiplication I can do it separately in a parallel processor. So it will be reduced in 1 by 6 time. Next is Flynn's classification for parallelism was proposed by researcher Michael J. Flynn in 1966. It is the most commonly accepted taxonomy of computer organization. So in this classification, computer are classified by whether it is processed in single instruction at a time or multiple instructions simultaneously, and whether it operates on one or multiple data sets. So there are four categories of Flynn's classification: SAST, which is single instruction, single data; SIMD, single instruction, multiple data; MIMD, multiple instruction, multiple data; and MIST, multiple instruction, single data. Okay, so we'll see each one in detail. So in SASD, These are called scalar processor, one instruction at a time. Each instruction have only one set of operands. So single instruction, only one instruction C means being extracted on the CPU during one clock cycle. So single data, only one data stream per dot cycle. So this is the this flow. So here, if you see this program, this is the example for this, single instruction and single data. So next is single instruction and multiple data. So here parallelly I can run multiple instruction working on single type of data. So this is it. If you see, this works on same data, this instruction also works on data. So this also works on. So the instruction is same, but multiple data in each cycle. Multiple instruction and single data. So here the instructions are different, whereas the data is same, that is provided. That is multiple instruction and single data. And in multiple instruction and multiple data, the instruction also is different, and the data is that is being worked on so are is different. Okay. So next we'll get into ARM, which is Advanced Risk Machine. So the T thumb in 16-bit instruction set, D on-chip debug support, M enhanced multiplier, and I embedded in circuit emulator hardware to give breakpoint and watch point. So ARM works on TDMI technology. So ARM features its RISC, that is a reduced instruction set computer, 32-bit general purpose processors, high performance and low power consumption, large and regular register file, load and store instruction architectures, pipelining is there, three address instruction is there, simple addressing modes are available. So conditional execution of instruction, control over both ALU and shifter in every data, multiple load and store instruction, co-processor instruction interfacing, and thumb architecture, then 16-bit compressed instruction set architecture. These are some of the features. So thumb instruction set, the T variant, recoded subset of ARM instruction, half the size of ARM instruction, which is 16-bit, greater code density, on execution 16-bit, thumb transparently decompressed to full 32-bit ARM without loss of performance, has all the advantages of 32-bit core, low performance and time critical code. So this is the core data model that is shown in the figure, shows a functional unit connected to data bus. So data enters the processor core through the data bus. So the data may be instruction to execute or data item. So the figure shows the von Neumann implementation of ARM. Data items and instructions share the same bus. In contrast, hardware implementation of ARM use different buses for data and instructions. So the instruction decoder translates the instruction before they are executed. So the ARM, like all RISC processor, use a load store architecture. That is, it has two instruction types for transferring data in and out. Load instruction copy data from memory to register, and store instruction copy data from register to memory. So data items are placed in register file, a blank storage bank up to 32-bit register. The sign extended order converts sign bit and 16-bit numbers to 32-bit values. So the ALU or the MAC takes the register value RM and R for A and B buses and computes a result. So one important feature of ARM is that register RM alternatively can be pre-processed in barrel shift before it enters the ALU. For load and share instructions, the incremented updates the add register before the core writes the next register. So next we'll see about ARM registers. So figure 2 shows active registers available in user mode, a protected mode normally used when executing application. So in figure 2, the shaded register identified assigned special purpose register. R13 is traditionally used as stack pointer, R14 is link register, and R15 is program counter. Whereas R3, all other are general purpose register. So there are up to 18 active registers, 16 data register, and 2 processor status register. So data register are visible to the programmer or not to R14. Depending upon the question, register 13 and 14 can also be used as general purpose register. In ARM state, R not to R13 or orthogonal, any instruction can apply to or not. You can equally well apply to any other register. However, there are instructions that treat R4 and R14 and 15 in a special way. So in addition to 16 register, there are two program state register, CPR and CPR, say SPSR. CPR stands for current program status register, and the SPSR for saved program status register. Next is processor mode. First 5 bits are signifies a mode selection. The processor mode determines which registers are active and access the rights of to the CPSR register itself. Each processor mode is either privileged or non-privileged. A privileged mode allows full read-write access. Conversely, a non-privileged mode allows read access to control field in CPSR, but still allows read write access to conditional flags. Six privileged modes are there: abort, fast interrupt request, supervisor system, and undefined. So abort mode, the processor enters abort mode when there is a failed attempt to access memory. Fast interrupt is this mode correspond to two interrupt levels available on the IRM processor. Supervisor mode is the processor is in uh, after reset and generally mode that an operating system kernel operates in. System mode is special version of user mode, full read-write access to CPSR. Undefined mode when program encounters an intent instruction that is undefined. User mode is used for programs and application. So instruction encoding, the ISA defines the format of an instruction, that is syntax, the meaning of an instruction, which is semantics. Format is encoding. So each instruction format has various fields. Opcode field gives the semantics. Operation fields say where to find inputs and where to find outputs. So MIPS instruction encoding is RISC ends fee 3 plus instruction formats. R in RISC is also stand for register. All instructions are of same length. Formats are consistent with each other. Opcode always at same place. R and RS are always at same place. And IMED are also always at same place. Load and store instruction. Mm, Load brings data from memory to register and store moves the data from register to memory to so back from memory to register. Each load store must specify the unit of info that has to be transferred through opcode. The address is in memory. The memory address is 32-bit address and instruction has 32 bits. So the address will be sum of a base register plus 16-bit offset, which will be immediate field and is added to the content of the base register. So examples of load store instruction: load word from memory LWRT offset, and store is SWRT and offset. So how to address memory in assembly language? So uh, how do I put base address in write register and how do I compute the offset? So first is most recommend let the assembler do it. In fact, the assembler generates the offset. So next is memory mapped IO. Each port is treated as the memory's location, whereas in IO port, each port is treated as independent unit. CPU memory address space is divided between memory and IO port. So separate address space for memory and IO ports. Single instruction can carry data from between memory and port. You need two transfer instruction to transfer. Data transfer is by means of instruction like move. Each port can be accessed by means of in-out instructions. Okay, so we'll get into the case study for ARM5 and ARM7 architecture. So data sizes and instruction set is 32-bit architecture. When used in ARM, byte means 8, half word means 16, word means 32 bits. Most ARM implement two instruction sets, 32-bit ARM instruction set and 16-bit thumb instruction set. JASL cores or can also execute Java bytecodes. So it has seven basic operating modes: user, FIQ, that is fast interrupt mode, and interrupt mode, supervisor mode, abort and undefined and system mode. So this already we have seen. So the ARM register set is current visible register in abort mode or these, and banned out registers are these. So in abort mode, these are the registers that is visible. In user mode, these two. In FAQ mode, this. And IRQ mode, this. SVC mode, this. And undefined mode, this. So system mode uses user mode registers, and it has two thumb state low registers and thumb state high registers. So ARM has 37 registers, all of which are 32-bit. One dedicated program counter, one dedicated current program status register, and five dedicated saved program status register, and 30 general purpose register. The current processor mode governs which of the several banks is accessible. Each mode can access a particular set of R0 to R2 register, a particular R13 stack pointer, and 14 link register and program counter PC and the current program status register. Privileged mode can also access public particular SPSR. So the program status register has conditional flags, a negative result from ALU, zero result from ALU, carry a ALU carried out operation, ALU overflow operation, and interrupt disable bits. I equal to 1 disables the interrupt, F equal to 1 disables the fast interrupts. Sticky overflow flags, architecture 5T and J only has its J architecture 5 day stage only, and T bit is architecture XT only. Mode bit specifies the processor mode. So program counter RFID, when the processor is executing in ARM state, all instructions are 32-bit wide. The program counter value is stored in bits 32, 3 to 31 to 2 with bits 1 and 0 undefined. When the processor indicates thumb state, 16-bit wide, off-wide aligned, and it is stored in 31 to 1, whereas 0 is undefined. When processor is executing in Zazzle mode, all instructions are 8 bits. Processor performs a word access to read 4 instructions at once. So constitutional execution and flags IRM instruction can be executed conditionally by post-specifying them with appropriate conditional code. This improves code density and performance by reducing number of forward branch instructions. By default, data processing instructions do not affect the consumption flow, and that can be outputted set by yes. The possible conditional codes are low, equal, not equal, unsigned higher or same, low, unsigned lower, and so the list is there. So branch instruction is branch condition label or branch condition subroutine label. So then the link build bit is the 24th bit and condition is 28 to 38, 31, sorry. So data processing instruction consists of arithmetic, logical, and comparison and data movement instructions. So arithmetic or add, ADC, sub SBC, and RSB, and logical or AND or XOR and BIC. Comparisons are CMP, CMN, TSP, TE2. Data movement is move and move on N. These instructions only work on register, not memory. So for multiply, MUL, MLA, UL, and so on. Basic mile instruction 2 to 5 cycles, 1 to 3 cycles on strong ARM, and 2 cycles on ARM 9. Above are general rules, refer to TRM for core things. So single register data transfer, memory must support all access sizes. Addressed access by LDR/STR is specified by a base register plus offset. This can be either added or subtracted from the base register. The software instruction is interrupt causes an exception trap to SWA hardware. The SWA hardware can expand the SWA number to decide what operation has to be performed. So PSR transfer instructions is again 32-bit. MSRS and MSR allow the contents of CPSR and SPSR to be transferred from general purpose. This is the sentence. So ARM branches and subroutine B and label. The label is the address of the branch, or BLN subroutine, where subroutine is the address of the branch, and it stores the return address in LR. Thumb is 16 bit instruction set, unlike ARM, which is 32-bit, optimized for code density from C, improved performance for narrow memory, subset of functionality of the ARM instruction. Core as additional executive state thumb. For most instruction generated by compiler, condition executed is not used. Source and destination register are identical. Only low register use. Constants are of limited size. So this is an example of ARM based system. This is how well ARM based system will look. So this is AMBA. AMBA is an ARM on-chip bus specification. The aim of AMBA are to make life easier for software designer. Standardize the bus interface, reduce the support required for ARM between internal design and teams, allow increased reuse of IP in design, enable the creation of upgrades and families of devices. Why use not the original ARM bus? Improve tools, support modularity, upgrading to other ARM cores. ADK is ARM's AMBA design kit, a generic standalone development environment enabling rapid creation of AMBD. ACT is complete environment for testing compilation of AMBA. The prime cells, the peripherals are set of AMBA compliant peripherals that are available for licensing from ARM. This includes a UART, real-time clock, keyboard and mouse, GPIO, and generic IR interface. Consult ARM website to understand about this. So with this, the fifth unit is done. Thank you.